Hey everyone, Neil deGrasse Tyson here. You know how much I love talking about the wonders of the universe, the elegance of physics, the sheer scale of it all. But today, we're going to bring things a little closer to home. We're diving into the world of engineering, where human ingenuity meets the unforgiving laws of physics. And sometimes, things go terribly wrong. We're talking catastrophic failures, the kind that make headlines and change history. But here's the thing about failure, it's the greatest teacher. Each of these disasters, as tragic as they were, forced us to re-examine our assumptions, refine our calculations, and ultimately, build a safer, more resilient world. Our first stop takes us back to 1628 Sweden. King Gustavus Adolphus commissions the Vasa, a warship like no other. This was a beast of a ship, bristling with cannons, a floating fortress meant to secure Sweden's place in the world. But there was a problem hidden beneath the surface, literally. The Vasa was top-heavy and unstable due to the king's demands for more grandeur. On its maiden voyage, a gust of wind capsized it in full view of horrified crowds. The Vasa became a monument to hubris, highlighting the critical importance of stability calculations in ship design. The year is 1937. The Hindenburg, a marvel of German engineering, is making its final approach at Lakehurst Naval Air Station in New Jersey. A fire erupted near the tail section, engulfing the entire airship in seconds. The Hindenburg disaster marked the end of the airship era, a stark reminder that progress without safety is a dangerous gamble. It forced the aviation industry to reconsider its reliance on flammable gases, paving the way for safer airplanes. Fast forward to 1981. It's a Friday evening at the Hyatt Regency Hotel in Kansas City, Missouri. Hundreds of people are gathered in the hotel's atrium enjoying a tea dance competition. Above them, two walkways spanned the open space. The upper walkway gave way, collapsing onto the crowded atrium floor below. The cause? A minor design change that doubled the load on the connection points. The Hyatt Regency walkway collapse led to stricter building codes and a renewed focus on safety in design and construction. January 28, 1986. Across America, school children and adults alike gathered around televisions to watch the launch of the Space Shuttle Challenger. Just 73 seconds after liftoff, the Challenger broke apart in the clear blue sky. Engineers had warned about the dangers of launching in cold temperatures, but their concerns were overruled. The Challenger disaster led to a complete overhaul of the Space Shuttle program, emphasizing safety and communication. Safety protocols were rewritten, and a renewed emphasis was placed on engineering rigor and independent oversight. Let's rewind to 1940 and journey to Tacoma, Washington. The Tacoma Narrows Bridge, nicknamed Galloping Gertie, was a marvel of modern engineering. Under a relatively mild wind, the bridge began to oscillate, twisting and writhing. Within hours, the structure ripped itself apart, collapsing into the waters below. The culprit? Aeroelastic flutter, a complex interaction between the bridge's structure and the wind. The collapse led to a revolution in bridge design, incorporating wind tunnel testing and aerodynamic considerations. April 26, 1986. At the Chernobyl nuclear power plant in Ukraine, a routine safety test went horribly wrong. A combination of design flaws and operator errors led to a catastrophic power surge. The reactor core overheated, leading to explosions that released radioactive material into the atmosphere. The Chernobyl disaster exposed the world to the devastating consequences of nuclear accidents. It forced the world to confront the dangers of nuclear power and the need for robust safety protocols and improved reactor designs. April 15, 1912. The RMS Titanic, the largest ship ever built at the time, set sail on its maiden voyage. On a moonless night in the North Atlantic, the Titanic struck an iceberg, tearing a series of gashes in its hull. The unsinkable ship began its slow descent into the depths, claiming the lives of over 1,500 people. The Titanic's sinking exposed the limitations of technology and the human cost of hubris. It led to sweeping changes in maritime safety regulations, including requirements for enough lifeboats and 24-hour radio monitoring. The year is 2010. In the Gulf of Mexico, the Deepwater Horizon oil rig suffered a catastrophic blowout. A surge of natural gas ignited, triggering a massive explosion that killed 11 workers. The explosion caused a massive oil spill, releasing an estimated 4.9 million barrels of oil into the Gulf. The disaster highlighted the environmental risks of offshore drilling and the importance of robust safety protocols. It led to stricter safety regulations for offshore oil and gas operations and a renewed focus on alternative energy sources. March 11, 2011, a magnitude 9.0 earthquake struck off the coast of Japan, triggering a devastating tsunami. The tsunami disabled the Fukushima Daiichi nuclear power plant's backup generators, crucial for cooling the reactors. With the cooling systems down, 3 reactors overheated, leading to meltdowns and explosions. The Fukushima disaster highlighted the importance of designing nuclear power plants to withstand extreme natural events. It emphasized the need for robust backup systems and clear communication in emergencies. Our final stop takes us to China, 1975. The Bangqiao Dam, a massive hydroelectric project, was pushed beyond its limits by Typhoon Nina. The dam's gates, clogged with debris, failed to release the mounting pressure, and on August 8th, the dam collapsed. The collapse unleashed a wall of water over 30 feet high, destroying entire villages and towns. The Bangqiao Dam collapse claimed the lives of an estimated 171,000 people. It stands as a stark reminder of the destructive power of nature and the importance of sound engineering practices. From the depths of the ocean to the vastness of space, these engineering disasters serve as stark reminders of the importance of human ingenuity, but also of the need for humility, rigor, and a constant focus on safety. Each of these tragedies forced us to re-examine our assumptions, refine our calculations, and ultimately build a safer, more resilient world. As we continue to push the boundaries of engineering, let us remember the lessons learned from these disasters. Engineering is all about trial and error. These disasters paved the way for safer, smarter designs that protect us today. What do you think was the worst engineering failure of all time? Let us know in the comments. If you enjoyed this video, don't forget to like, share, and subscribe for more mind-blowing stories from the world of engineering.